Today we'll be talking about carboxylic acid functionality groups. Looking at their nomenclature, we will be following most of the nomenclature that we have learned in module 4 of 2210, that you will first find the priority group. In this carboxylic acid, the carbon of carboxylic acid will always get number 1. The second thing that you must look for is the longest chain. So if we look at the structure, our longest chain is right here. So the name will go something like this. Because of 8 carbons, we will have the oct. Throughout, it is an alkane, ene. And instead of an E, the regular E, our priority is the carboxylic acid, we will now have oic acid. Number 5, locant value has an ethyl group. So the name of this structure would be 5-ethyl octanoic acid. Similarly, if you have a structure which looks something like this, in presence of carboxylic, OH will be just an substituent and its name is hydroxy. Again, carboxylic carbon will get number 1, 2, 3, 4, and 5. So this is pent throughout alkane, oic acid. The rest will be alphabetical. The H from hydroxy and the C of the chloro. So 3-chloro, 4-hydroxy, pentanoic acid. There are some compounds which will have common names also. For example, when you have a carboxylic acid on a benzene ring, we call it a benzoic acid. And the most common carboxylic acid that we see is with these 2 carbons, known as the acetic acid. Then we have phthalic acid, and so on and so forth. Now, as the name suggests, carboxylic acids are acidic in nature. If you react carboxylic acid, you are going to get an acid-base reaction. Whereas the most acidic hydrogen on carboxylic acid, which is right here. So why is this hydrogen acidic? And you should be able to figure out acidity of different carboxylic acids compared to each other and compared to other groups also. So remember, whenever we talk about acidity or acidic nature, we always look at the ARIO factor, the atom, possibility of resonance, induction, and orbitals. And if you look at our carboxylic acid, it is following everything. The hydrogen, the acidic hydrogen, is attached to a very electronegative atom. There is a possibility of resonance, which makes this hydrogen even more acidic. And then the sp2 orbitals. Remember, smaller the orbitals, the closer they hold the negative charge to the positive nucleus. So 50% S in case of sp makes it very, very acidic compared to sp2 orbitals, and sp3 orbitals are the least acidic of them all. So thinking about it, if I compare these two, because of induction, this molecule or this hydrogen will be more acidic. Okay. While we're talking about the nomenclature, I just wanted to point out to you that sometimes you will see a molecule like this, where the hydrogen is missing in your, these are known with O8. So instead of calling them as a oic acid, their names end with O8. So for example, this is sodium 123 propanoate. And this will be methyl 123 propanoate. So looking at the synthesis of these compounds, the carboxylic acids, we have already looked at a couple of the structures, reactions already. So for example, if I have an alkyne and I subject it in presence of ozone, I can use zinc or water or DMS or sodium bisulfite. A cleavage will occur and carboxylic acids of these two varieties, this carbon, will appear. If we have a terminal alkyne and I use these conditions, either of these solvents, cleavage will occur right here and I will get carbon dioxide gas along with the acid that will be produced. Another reaction that we have already seen is in presence of a benzylic hydrogen. And no matter how long those chains are, then if you use chromic acid or hot KMNO4, our side chain will oxidize. Now remember, the presence of this benzylic hydrogen is important. If I do not have this benzylic hydrogen, no reaction occurs at that point. Another reaction that we have already seen are the regular oxidation reactions. So when you have a primary alcohol and you use chromic acid or sodium dichromate, your primary alcohol will become the carboxylic acid. A new reaction that we will see in this chapter is when we have hydrolyzed nitriles in presence of acid and heat. Okay, so this is an important conversion as well. So this carbon right here, this carbon becomes or hydrolyzes to carboxylic acid. Another newer reaction that you have seen in this chapter would be using a Grignard reagent. This is diethyl ether. You can also use THF. Both of them are ether solvents. The magnesium gets inserted between the carbon and the bromine. And now when you introduce carbon dioxide and a proton source, we will get an extra carbon. So this carbon dioxide is going to become carboxylic acid. So what we have done, we have increased the number of carbons during this process. The next part of this is, let's look at the reactions of carboxylic acids. Okay, so I'm just going to use a common starting material, and if I subject this starting material to sodium borohydride followed by water, what will happen? We have seen sodium borohydride only reacts with aldehydes and ketones. It will leave the carboxylic acid alone, so no reaction occurs. On the other hand, if we use lithium aluminum hydride in presence of followed by water, now we are going to see this carbon reducing to a primary alcohol. A newer reagent that you will see is the diol. Now in this particular reducing agent, your carboxylic steps down and becomes an aldehyde. So it does not go all the way to the primary alcohol. It stops at the aldehyde site. Similar to what we have seen in alcohols, if we use SOCl2, it will replace your OH, generating an acyl halide. Similarly, if you use PBr3, the Br will replace your OH, and you will have a different kind of acyl halide, in this case, a bromide. Another new reaction that you would see here is when you have an alcohol in presence of acid. A Fischer esterification reaction will occur, and this oxygen will get rid of this hydrogen, and your alkyl group gets attached here. So you are generating an ester. You can also generate an ester in presence of a base, but in that you will have to use the base first so that you can get rid of the acidic hydrogen and generate a sodium propionate at this point. So with the O negative, it will attack your alkyl carbon and kick out the leaving group. Another important reaction that comes to my mind right now is the malic acid. So if we have a linear kind of a dicarboxylic acid. So this is malic acid in presence of heat will lose a water molecule and generate an anhydride. But this kind of internal cyclization is only possible if you are getting a 5 or 6 membered ring. So only a 5 to 6 membered anhydride can be possible on heating a dicarboxylic structure. If we have a hydroxy acid, which looks something like this, and now subject this to acidic conditions, you are going to get internal cyclizations. This would be a cyclic ester, which is known as a lactone cyclic ester. Again, this will be possible only when you are getting a 5 to 6 membered ring. And I just want to remind you, how do you get the hydroxy acid back? In presence of a base. You can just use sodium hydroxide or potassium hydroxide, and this lactone will open up back to its hydroxy acid. If you have a functional or a substituent on this, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. So the the methyl is on the 3rd carbon. So don't get worried if you see a substituent on structures like this. Another thing that you need to know in this particular module is your reactivity order of the derivatives of carboxylic acids. So the most reactive derivative of carboxylic acid are your acyl halides, okay, followed by anhydrides, followed by esters, followed by amides. Okay. Now, the reactivity depends on several factors. For example, where is the induction going on? What kind of a leaving group you have? You see the chlorine and oxygen both make this carbon very, very electrophilic. And this chlorine is a weak base, which makes it a great leaving group. If you look at the amide, there will be a resonance, internal resonance that is present in this structure, which stabilizes this carbon, this electrophilic carbon, and makes this less reactive. Moreover, if you look at the leaving group, NH2 negative, it's a very strong base. A strong base is a weak leaving group or a bad leaving group. So besides induction, resonance, and sterics, of course, the kind of leaving group that you have will also affect the reactivity. From your stronger derivatives, you can make the weaker derivatives. But from a weak derivative, you cannot make the stronger derivatives. And another interesting thing is all of these derivatives can be converted back to carboxylic acid just by hydrolysis. You may have to use a stronger acid sometimes you might have to use heat, but in general, you can get the carboxylic acid back. So let's look at the acyl halides, which are the most reactive of them all. So with the molecule like this, I'm going to get this oxygen to attack right here. The carbonyl will open up. And then followed by regeneration of carbonyl kicking out of the chlorine, I will get a reagent or a product like this. COOH. What is this functional group? It's an anhydride. Yeah. So instead of this sodium acetate, if I have sodium methoxide, again, the O is going to attack here, opening up of carbonyl will take place. This will be followed by the regeneration of carbonyl kicking out of the leaving group. And we will be generating a ester. You can also get an ester from the acyl halide by using the corresponding alcohol and a weak base like pyridine. So in this case also, we are going to get an ester, OCH3. When we will use two molecules of ammonia or two molecules of any amine, again, we are going to get a nucleophilic addition kind of a reaction. CH3, CH2, CONH2. CH3, CH2, CONH3. So we can generate amides from our acyl halide as well. Again, looking at the reduction reactions, only with lithium aluminum hydride, we will see any reductions, not with sodium borohydride. We will be getting a primary alcohol. But if I use diol for reduction purpose, I will end up with an aldehyde. So look and keep in mind the different functional groups that you can get starting from your acyl halides and from other functional groups also. Let's now try to add on a Grignard reagent here. So because it is next to the magnesium, this gets a negative charge. And a similar attack will occur. Oops, CH2. But with Grignards, carbon negative, C negative is a very strong nucleophile, you will end up with a tertiary alcohol. So this is with Grignard's. You also have a Gilman reaction that is possible. But Gilman is a little restrictive. You will not end up with so we already have these 1, 2, 3. Oops. So 1, 2, 3 from your starting material, and then 1 CH3 from your reagent. What is this functional group? A ketone. And hence, you can see how versatile these acyl halides are. Okay, so the next are the reactions with anhydride. So again, I'm going to take a very generic kind of an anhydride. It's a symmetrical anhydride, and under presence of acidic conditions and a lot of water, we are going to hydrolyze it into 2 molecules of acetic acid. So there is 1 carbon here, 1 carbon here. Similarly, if I will use my base, sodium hydroxide, followed by acid, I will still hydrolyze it into the 2 molecules of the acetic acid. So hydrolysis either during acidic conditions or using basic conditions will give you your starting carboxylic acid. You can also use these conditions to create an ester, methyl acetate, acetinoate. In presence of amines, we are going to get amides. In presence of Grignards, we will get our tertiary alcohol. 1, 2, CH3, CH3. So these 2 are from the starting material and these 2 come from here. Again, with Gilman reagent, I will get my ketone. With lithium aluminum hydride, primary alcohol, and with lithium aluminum alkoxide, trialkoxide, I will get the aldehyde. Two, two. So again, as we see, our anhydride can also have a variety of reactions. Looking at our esters, and let me use again a generic form of an ester, COOH3. Let's first look at the hydrolysis. Acidic hydrolysis, excess of water, you are going to hydrolyze this. The carbonyl part into carboxylic acid, and this part as your alcohol. Similarly, in presence of a strong base, followed by protonation solution, we will get H2. Exactly same thing. So the hydrolysis of esters also generates the starting carboxylic acids. Because esters are stronger than amines, we can synthesize amides. CH2CH3. We can create amides from esters, but this is going to be a slow and literally ineffective kind of a synthesis. So for the generation of amides, we usually don't use this process. We generally use the acyl halide. The acyl halide in presence of amines can generate an amide very fast. Looking at the Grignard reaction, again, we're just going to attack this. You're going to get your tertiary alcohol. Using lithium aluminum hydride. We are going to get our primary alcohol. H. Using diol. We will get our aldehyde. Oops. So very similar reactions to what we have already seen. The reaction of amides. So if you look at amides, one of the first things that I wanted to point out to you was just like we had cyclic esters in form of lactones, we can have lactams from amino acids. So let's say I have a amino acid 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. And so this amino acid, the amine and the acid part, can cyclize and give you a cyclic amide. Just like your cyclic ester, this will only work if you are getting a 5 or a 6-membered cyclic lactam. The cyclic amides are also known as lactives. And when you will hydrolyze because of this amide's low reactivity, you will need to hydrolyze it with heat. And then you will generate your original carboxylic acid. There are two new reactions that you would have seen in this reaction. So instead of giving you a primary alcohol, and let me use the same. If I have a structure like this and I want to reduce it, in the past, we have seen whenever we use lithium aluminum hydride, we generate a primary alcohol, starting from the derivatives of carboxylic acid. The difference here is when you have an amide and you're using lithium aluminum hydride, all that happens is the complete reduction of this carbonyl. So we will have this CH3CH2. And instead of this C, I will now have a CH2. The rest of the group stays the same. So this is a newer kind of a reaction and a different kind of a reaction for lithium aluminum hydride and the carbonyl groups. Another reaction that is a little different is when you have an amide and you use SOCl2. Now, if you remember, we just did SOCl2 where the Cl replaces the OH. That's all that Cl does in SOCl2. But when you have the amide and you have SOCl2, you generate a nitrile. Again, a little different reaction from others that we have seen. So the last part is the reactions with nitriles. Just like other derivatives, when you hydrolyze this in presence of acid and heat, you are going to get your carboxylic acid 1,2, 1,2. You can also use basic conditions. First, introduce your basic conditions, followed by acidic conditions for protonation. You're going to get your starting OH. And yes, another newer reaction that you would have seen is with lithium aluminum hydride when you have a nitrile. Star here before we actually do it. So this is CH3, this is C, this is N, and you will reduce both of them and add all the hydrogens that are possible.